Welcome to Wireless Future. This is episode 39. I'm Erik Larsson, and I'm here as always with my colleague Emil Björnsson. Hello, Emil. How are you this morning?
I'm great, as always. It's always nice to talk to you.
Indeed. And this morning we have a guest, Parisa Aghdam. Parisa works at Ericsson Research in Gothenburg, so this is like a triangle recording with Stockholm, Gothenburg, Linköping. And Parisa is the technical lead of a European-funded project, 6G Tandem, that develops radio stripe technology for Terahertz. Hello, Parisa. How are you this morning?
Hello, Erik. Hello, Emil. I'm doing good. Thank you. It's really an honor to finally get to be with your podcast that I've been a huge fan of.
Well, it's great to have you, Parisa.
Thank you.
So, where do we start, Emil? Radio stripes.
Yeah, I think this is sort of a
terahertz.
good opportunity to not only hear what an individual researcher is working on, but really sort of the concept behind some of these real 6G projects that are happening, and then particularly the one that you are leading here. So I'm looking forward to the conversation.
Yeah, and I've been thinking about MIMO technology and massive MIMO especially. I mean, massive MIMO is like air, right? It's everywhere, but nobody talks about it. It's like we don't sit here talking that we have air around us, but we have massive MIMO around us since when did the commercial deployments actually first happen, Emil?
19, I think. Something like that?
Yeah, something like that. So more than 5 years. Huh? So we have massive MIMO as a core technology in 5G. And then the question is what the next step on this technology journey is going to be. And there's currently a lot of talking in, I think, both in academia and industry about distributed massive MIMO, and cell-free massive MIMO is another term for the same thing, where the idea is to spread out the MIMO antennas geographically and put them in the form of antenna panels on the wall, or put them in some other distributed configuration. And I think a particular way of deploying distributed or cell-free MIMO that's been discussed a lot is known as radio stripes, where the idea is that we basically build like a long cable, and along this cable there will be antennas or antenna units, and then we can hang this cable or well, nail it to the wall or put it somewhere where it fits in. And radio stripes are now being taken to the Terahertz band. That's the project, Parisa, that you're leading.
Yes.
So where are the challenges here? How is this supposed to work to start with? And what are the challenges in building radio stripes at the Terahertz band?
Yeah, well, to start with, I think one of the most important factors is the hardware cost. Given that at very high frequencies, at sub-terahertz specifically, the harsh environmental propagation characteristics of sub-terahertz make these deployments very sensitive, right? So you need more antenna elements, you need more radio units, as we call it in 6G tandem. So the hardware cost of them can be huge in specific cases, because you need, specifically it's a line of sight that is mode of propagation here that we are specifically looking for. So you need more units to be closer to the EUEs, the user entities, the devices, the handsets, and also that then these many devices that need their own self local oscillators need to be phase synchronized. That was where we thought of the radio stripes, actually, that you will have a central unit, central tandem unit we call it, or central processing unit, that you generate the high frequencies, the sub-terahertz frequencies, and you send the signals towards these radio units.
Mm.
So do you sort of overcome the problem of generating LO signals in each unit, which makes it more complicated, more expensive. So yeah, that is one of the problems. We see that again, sub-terahertz signals they have issues with the blockage. When you have these higher frequencies, you have higher losses, right? And then you need more antenna elements. More antenna elements means you have tinier, smaller beam widths, and then you need more beam forming. Yeah.
Mm. So you're basically summarizing the challenges of terahertz operation here, right? Of course, we have very high Dopplers, so it'll be difficult to track the channel
yes.
and all of that. But then maybe even worse, and more importantly, we have a high path loss.
Yes.
And propagation is mostly line of sight, so propagation paths will be very sensitive to blocking. And then on top of that, there is the difficulty of phase synchronizing local oscillators that are situated far apart. And this is where the Tandem project comes in and basically generates a signal centrally and distributes the signal through multiple antenna units over a radio stripe.
That is great summary.
Right. So there's obviously a lot of technical challenges to overcome here, which of course makes you wonder, why do we even want to overcome such things like this? So this is an EU-funded project, and I was trying to submit some competing proposals in the last years, and which didn't go through. And I think some of the thing is that you really need not only technical challenges, but a good vision and objective of a project like this. So what were these objectives for this 6G tandem?
Yeah, well, I mean, the Tandem project, the Tandem name comes from the fact that we envision combining a sub 10 or sub 6 gigahertz radio base station, radio access, together with the radio stripe concept operating at sub terahertz frequencies. So that is the main description of this dual frequency project aiming for 6G applications. And the main and most important objective is, well, currently there are multi-carrier deployments, of course, but they work one frequency at a time. And oftentimes these combination of dual frequency is not really optimized. And our aim is that we take advantage of the reliable communication of lower frequencies and tap into the very high data rates of sub-terahertz deployment. So there will be a great marriage of these two frequencies. And also the second most important thing about 6G tandem is the radio stripe concept, where we envision that it will be a cost-efficient, easily deployable distributed MIMO system, where you, this is how I envision it personally, that you are going to have a Taylor Swift event in an arena with a huge, it's a huge event, many number of users, densely populated in the small area relatively. And then you envision that, given that in the future use cases, there will be XR applications, for example, you need high data rates, you need really reliable communication. You have your sub 6 or 3.5 gigahertz like radio dot type of access points in like Ericsson's radio dot, I mean, and then you say, okay, we are not going to make it with these. So someone comes and puts the fibers on the ceiling, on the walls, and then you have this system operating optimally. So that was our vision with 6G tandem.
So it's really this tandem operation where there is a sub 10 gigahertz network that provides base coverage, and then the terahertz radio stripe on top of that offers spot-wise enhancement, but with very high, spot-wise enhancement of the coverage, but with very high data rates.
Right, and I think the word tandem is particularly well used here. I think a lot of abbreviations that you find for projects might not really mean much for the actual project, but I think, today you could deploy a millimeter wave base station at one location and a massive MIMO base station in sub-6 at some other place, and in a way they will take care of coverage and capacity in different ways. But here you really co-locate them, and you have the vision to use information between the different bands to really let them work in tandem
within the very same coverage area.
Yes.
Right. So now let's talk about radio stripes and the way that these RF, because actually for the terahertz operation, it is the actual RF signal that will be carried on the stripe, right? There'll be a central unit that generates the RF using a single LO or local oscillator, and then it's the actual RF signals that will be carried over the stripe. So here's my mock-up of a terahertz stripe. This is a 8mm, I think, the sort of plastic hose. And I think it serves well to illustrate the concept of the stripe, because this is more or less what they're going to look like, right? I'm not sure about the diameter of the final thing. It might be slightly thinner than my plastic hose here, but it will be connected at one end to a central unit that generates the RF, and then it will be attached, nailed to the, ceiling maybe, or hidden somewhere. Oh, can't be hidden, I suppose, because there has to be line of sight, right, too. And then every meter or so, there will be a small radio unit attached to it. And the radio unit will contain some antenna patches. It will contain maybe some switches and some very basic electronics, but nothing coherent, right? So no LO or anything. But it will have to contain an amplifier, because the stripe itself, it carries the terahertz signal, and that stripe attenuates the signal such that every meter or so the signal has to be re-amplified in order not to get lost when the stripe gets long. So could you speak to what are the advantages of the stripe architecture, and particularly, so my understanding has been that the stripe itself that will carry the signal, it'll be plastic, in fact. It won't look like a hose exactly, but it will have a plastic core, and then it'll have some cladding around it and maybe some other materials. Could you speak to what the advantages are of this carrying signals over a plastic stripe like this?
Yeah, so maybe I can start with the fact that these plastic microwave fibers, as we call them, or dielectric waveguides, are simply, as you say, plastic waveguides. And their basic functionality comes from the total internal reflection, where you have your dielectric core, and then you have your foam cladding or whatever type of cladding. The core can be 2 millimeter by 1 millimeter, rectangular core, and then you talked about the cross-section dimensions. It might come to few millimeters in diameter.
A few millimeters. So let's recap. Just for for me and for the audience, maybe that. So wavelength here, we're talking about, so let's see, so 1 gigahertz is 30 centimeters. 10 gigahertz is 3 centimeters. And when we say terahertz, really we mean sub-terahertz, we mean maybe 100 gigahertz, which is then 3 millimeters. So the diameter of the core of the plastic fiber here actually carries the RF signal. It has a diameter on the order of the wavelength. Is that right?
That is correct.
Yeah.
Yes, indeed. And maybe I missed this information. The frequency band we are aiming here is D band, is between 130, 170 gigahertz roughly. Of course, we have some specified bands there. So it's roughly 140, 150 gigahertz central frequency.
Right, so wavelength is about maybe
Even
1 or
smaller.
2 millimeters, something of that sort, yeah.
Yes. Yeah. So
Right.
exactly.
So is this like the fiber that we use for optical fibers, internet connections, but at a different scale, or is this something entirely different?
That is a great question. So this is no optical fiber. This is plastic fiber, as you say, and the core material it can be PTFE. The cladding can be polyethylene PE. So there is this. I like this diagram. There is this link efficiency on the y-axis, and then you have the distance. For lower distances for communication, you have the copper, and you have the link efficiency very high. Then you also have these VCEL, right, type of lasers, as you say, optical fibers for very high distances. Like the whole planet is connected by optical fibers, right, with high data rate communication. But when it comes to the mid-range and towards short-range communication, where with the application of data centers, when you need hundreds of gigabit per second, or the car, the automotive communication, the communication in the car, which is between 5 to 15 meters roughly. There, we don't have a clear solution with this type of waveguides. So optical fibers are very high data rate, high power consuming for these applications. You need the silicon sources, right? And then for that matter, you need the interconnects, which are very expensive. You need the micrometers alignment with the sources, right? So which makes it very, and also very temperature sensitive. They are, so they are not really good for data centers and these medium short range applications we are aiming for. And so these type of fibers, the ones that Eric was showing, are perfect because you have very small dimensions at very high frequency. So higher than 70 gigahertz, the dimensions become smaller and smaller. You don't see them if you deploy them on the walls and ceilings. And they are not sensitive at all to misalignments. It's a few hundred microns we have tested even. And the only problem is the losses. That's what we are trying to engineer, employing new materials, new ways of implementing the fiber. There are these hollow core fibers. That you have struts that holds the whole core. So I mean, the engineering problem there is to lower the losses. Yeah.
To lower the losses. I mean, so you mentioned materials here and PTFE, I think in particular. Yes. I mean, to the layman, this is all plastics, right? Like a PET bottle. Yeah. So I guess another thing here is that the fiber, even though, I mean, it might end up looking like something of this sort here, like the plastic hose, you would also need to carry like some electrical wires along, right, to operate these, because there will be switches at the antenna units. There won't be, and there will be amplifiers, more importantly, that need a power source. So would those be powered like through an electrical little line that goes along with the fiber, or could they be powered somehow from the RF signal itself, or how is that envisioned here?
That's a great point. Actually, our vision was that at some point, maybe at the end of the project, towards the end of the project, we will have an answer to that, because you want to have some copper lines, right? As you say, for the power, for maybe digital processing, if you need to be able to integrate it into the fiber. For this project that we are having, I don't think we will be able to do that. We will probably have PCBs that will power up our circuits. So our circuits will be packaged and then will be sitting and assembled on the PCB, and then the fiber will come towards that. So maybe you can even use the PCB as a holder of the fiber.
Yeah, sure. I mean, there'll be PCBs at any point. Like there is an antenna unit, there'll be a small PCB, there'll be a small patch antenna, there'll be a switch and an amplifier.
Yes.
And the amplifier now, importantly, not to amplify the signal that goes out on the air, right? But rather to amplify the signal that continues on through the stripe to the next antenna unit, because as you already alluded to, the RF signal will become attenuated as it travels through the stripe.
True. Yes.
Right.
Yeah, we have identified two type of units in our project. One is the radio unit. As you say, we will have amplifications and PAs and LNA switches, TXRX switches, and so on for the radiation part of it for the antenna. But we also have defined a booster unit where you don't necessarily have to have the antennas, only to boost the
Only to
signal.
boost the signal to it's a repeater on the stripe, more or less.
Exactly, because we see that, as you say, the losses are quite high. Reportedly, it's between 2 to 5 dB per meter.
2 to 5 dB per meter. That's quite a lot. I mean, imagine 10 meters of stripe, then that would be like 20 or up to 50 dB loss.
Yes. So that's why this is how we have thought about this, that, well, we will come to that later on, but these units are done in silicon, germanium, and they are quite cheap. And the idea and the vision for the future is that those units will somehow be integrated in the fiber, that you just have the fiber. You don't even have these intermittent parts. Right. You don't see it, at least.
So it really looks like
exactly the vision, at least.
Right. Yeah. So how will this integrate with the sub 10 gigahertz macro system? Emil, right. I think.
Yeah. So. I mean, in principle, maybe I should first ask you the question. So if you want to send now signals at both the sub-terahertz and at the lower frequency, do you need to have different waveguides for this? Or is it the one and the same?
Oh, you mean if... no, I mean, the plastic waveguide is only intended for the sub-terahertz.
Right, so for the lower frequencies, how do you integrate that into the stripe?
By lower frequency, you mean the macro stage?
Yeah, exactly.
Okay. No, I mean, they are independent systems, right? So, so let's say we have these radio dots working at 3.5 gigahertz, and then you have your separate central unit which feeds in these fibers. And our envision system is that you will have these separate fibers that are being fed from the central unit, and then in each fiber you have several of these radio units which have this amplification and patch antennas. And I can maybe mention this, followed up by Eric's point on the losses and how many units you need to have, for example, on the same fiber. To begin with, we thought maybe 10 meters apart they can be. But then when we did the calculations of the amount of power you will have, that you need to have at the input of each unit, and we have set some limits, like let's say 25-30 dB for each unit, because this sort of limit is imposed by the fact that you have very short distances between the input and output, and you will probably have leakage, right, and crosstalk and coupling, and which makes it, if you have very high gain, then you will have self-oscillation. So let's say you have a limited power, limited gain there, and then you are trying to see, okay, we have, let's say, 5 dB or 4 dB per meter of loss. At what intervals you need these units? So we came to a number 5 to 6 meters at most. You cannot tolerate more than that. So at current state, we are thinking 1 to 3 meters that we repeat these units. And then this sort of also poses the requirements on the system, antenna coverage, services, everything else.
Right. And if you now have multiple antennas along this stripe here, you want to send different signals from them, can you still send these signals over the same waveguide?
So, okay, that is another point, true. We have only we have decided to have one antenna unit on per like serving.
Right. So that's why there is a switch, right? At every antenna unit there is a switch. Yeah.
I see. So it's like an antenna selection.
Yeah, it's
system
like
then.
an antenna selection in
Exactly.
that respect.
All right, so let's go back then to the question. So I guess if you deploy a system with two different frequencies here, one macro and one sub-terahertz frequency, then the simplest implementation of this would be that there is a scheduler somewhere who decides is a user in system A or in system B, and then maybe if you're blocked, you are moved down to the macro. But now if you want them to work more in tandem with each other, how deep can you or what can you exploit by letting the systems work together?
Yeah, so I think we have some previous studies that they have done regarding the tandem operation. For example, there's been this study where they had this digital sub 6 gigahertz macro station where they tried to exploit that for extracting spatial information of the users, which you then feed it into the sub-terahertz system, right? Then you can have some machine learning processes trying to identify blockage, which beam to use. So as you say, this can be sort of one way that these two work together, these two frequencies. So yeah, I mean, we haven't come that far yet with the project. Now we are marking the first year of the project, but that is the aim, that we see how they can work together. It should one frequency have only data, the other one maybe the sub-terahertz only carrying data, the other one can have the controlling of the signals. The mobility information maybe comes from the sub 10 gigahertz.
Right. So you were mentioning that you've been running the project now for 1 year. So what kind of result do you have so far? Maybe use cases is one of the things that you typically
yes.
start with in a project like this.
Indeed. Yes. Actually, our the first two deliverables that we had was about the use cases and the required models for the future of this project. So, and the use case identification was really a sort of exhaustive work we did.
Wow.
So we started with scouting use cases from predefined projects like HexaX, Reindeer. They had a collective of use cases. We started with that. We started with what we think the healthcare system, the entertainments, and the industries will be needing as a 6G use case, and also sort of try to adapt it to what 6G tandem can also deliver. So we started with categorizing the use cases with either they should be AR, VR, XR, ultra reliable low latency communication, high data rate communication, non-latency critical, and positioning and tracking. So we sort of try to divide them in categories.
Right. Yeah. And I mean, my impression from maybe based on the fact that deployment on millimeter wave for outdoor coverage have not really been so successful in the world. It seems like it's this kind of use case that you have been mentioning for indoor system or systems in a particular confined area, or like the Taylor Swift concert kind of situations where you really have a lot of line of sight, but you might have very specific system requirements. Is there a specific use case that you think would be the first one where one would deploy a system like this?
Personally, again, I think maybe our partners from 6G tandem might have different opinions, but to me, the enterprise sector where we have these industries like car industry, for example, will really take advantage of such systems. Because when it comes to the production lines or assembly lines, if they are wired, if you need to make changes, this will cost a lot for the industry. And also, we see that, for example, the car industry, where they are producing a car which is worth $20,000 to $80,000. If there is a glitch in the assembly line, every second will cost them thousands of millions of dollars. So we see that this system can really help automating industries, because then you need a quite huge number of data rates, latency, high resilience, and high reliable communication, which we can get from these two systems working together.
So before I let Eric ask some more technical questions, I also want to ask you, what kind of set of partners do you need in a product like this to go all the way from system concept to hardware design?
Yeah, that's a very good question. I think this is, I have worked, as I said, with testbeds and pre-dev activities, but 6G tandem is quite one level higher in the sense that it's very demanding to find the right profiles, and we have them. I mean, we have the communication system and signal processing colleagues. We have you have the hardware expertise from Infineon, Huber and Sooner. We have, Ericsson is here. We have had colleagues working with the link budget analysis and system requirements. And Eric's, Lisbeth's, and we have Lund, we have Uwe Edfors. Everyone is really coming in with their expertise, and it's a wide spectrum of expertise. It can be antenna design. We have just a colleague there with their PhD students working on. So multidisciplinary.
It's multidisciplinary. It's
Yeah, we will put a link to the project and list out the project partners also in the description of this episode.
We should, Emil. Yes. So it's an amazing project to be in Parisa.
Indeed.
We talked about quite a bit about frequencies here, right? And the fact that these drives would operate in these sub-terahertz, which is somewhere, did you say 140 or 170, something of that sort, gigahertz. What bandwidths do you envision that the signals would carry here? Because the bandwidth would ultimately, of course, there's abundant bandwidth at these carriers, but the bandwidth would also ultimately determine the data rates that we could get.
That is correct. Yeah, we always say we go for sub-terahertz for its untapped frequency spectrum, and we start with saying that D-band has 130 to 170 gigahertz, but of course it's not like that. We have defined bandwidths there. Even in D-band we have, if I'm not mistaken, 140 to 148 gigahertz, and also 151.5 to 164, for example. Those are the bands that we are at least looking at here in Tandem project.
So then this means bandwidths on the order of between 5 and 10 gigahertz. So if you just think like conventionally in comms theory, I mean, if you have a spectral efficiency of 1 bit per second in hertz, then in a 10 gigahertz bandwidth, you would get across 10 gigabit per second, right? And now, obviously, this will all rely on line of sight propagation, because at terahertz there aren't a lot of reflections, or are there, that we can exploit? I mean, do you know that, Emil? I mean, in terahertz propagation, my understanding has been that mainly we will have to be in line of sight of the antenna panel and to get any coverage, right? So you're sitting there in your stadium, you would have line of sight to Taylor Swift, and you would have line of sight to the radio stripe antenna panel, and then get your 10 gigahertz or gigabit of data per second to upload streams. So let's get a bit more technical. So we talked earlier about losses, and you mentioned some figures. I think you said, did you say between 1 and 5 dB per meter, or between 2 dB and 5 dB, 2 to 5 dB per meter in loss, which means that we need to put amplifiers there, right? Every meter or every few meters at least. what is a typical output power of an amplifier? If we take like state-of-the-art hardware today for this sub-terahertz band, how much can they feasibly generate before they get too hot or just infeasible to build?
I think for this technology that we have in this project, PSAT is 10 dBm.
10 dBm, so that means
it can be between 5 to 10.
Yeah, 10 dBm is 10 milliwatt, right? So rather small power levels, indeed. So will the stripe bring any other problems? I'm thinking of like ideally it should be a linear and time invariant device, right? I mean, it does attenuate the signal, but would it also introduce any dispersion to any significant degree?
Yeah, I think the dispersion that well, I mean, it certainly introduces dispersion.
Yeah.
And maybe group delays of maybe some picoseconds over few tens of gigahertz.
Yeah, sure. Okay. So now this is getting very quantitative here with, let's say, numbers that could be difficult to relate on the fly. But there'll obviously be a time delay, right? Because the signal travels more slowly within the fiber as compared to through the air. But there might also be some, in fact, dispersion in that the phase characteristics isn't linear over the band, and not even the amplitude characteristics. But that presumably could be handled by equalization or pre-compensation of the transmitted signal, right?
Yeah.
Now that we have amplifiers, obviously at the central unit, but also like every meter or so along the stripe, will there be significant nonlinear distortion introduced here that needs to be dealt with? I'm thinking of like nonlinearities is typically something we want to avoid, right? And the main source typically is in amplifiers. So to avoid or to minimize the impact, and either we back off the amplifier, which costs us a lot of power or link budget, or we increase the circuit complexity to make them more linear. And typically in wireless comms, this is a big deal because we want to avoid out-of-band radiation and keep to out-of-band radiation limits that are set in the standard. But how will this be for terahertz? Is nonlinearity or nonlinearities in these amplifiers going to be a big deal or not?
Well, as you say, maybe I can start with the power. As you say, it's quite low power they are generating these PAs. Then, depending on how we are setting up the system, you may need to do backoff or not. And then closing to the saturation, of course, you may introduce more and more nonlinearity, and you might, disturb the signal. But we did our Chalmers colleagues did a very intense sort of a study to see how many, if you have so many, for example, units, would this wreak havoc on your signal, or would it be the nonlinearities or the losses? How should you like?
There'll be a
what is the trade-off?
Yeah, it sounds like there'll be a trade-off here, right? I mean, we could decrease backoff, and that will bring more distortion, but it will help the link budget, and vice versa. So there's a complex interplay between different design choices here in terms of what amplifiers to use, what operating points to select, how often to, or how frequently, or what spacing to put the amplifiers, and so on.
Yes.
So now these plastic fibers that carry the signal, ideally, I suppose, you model these using electromagnetic theory, you would model them as perfect cylinders, right? Or just straight like this. What happens if you bend the fiber? Because if you take a regular like signal carrying cable, a coax or something, and you bend it, and the radius of the bend here is comparable to the wavelength, then what happens is the signal start to leak out, right? So is that any significant phenomenon or effect on the terahertz stripe, or could we basically, what will it be like? Will it have to be just totally straight like this, or could it be like deployed in some kind of snake-like shape, or could you?
Well, as far as I have understood from our Hoover and Sooner partner, so they say that this is a multi-parameter trade-off when you design the fiber. So you have the dispersion, you have the losses, you have the bending radius as well, the rigidity of the fiber.
Right. But what would be like a typically allowed bending radius? Do you have a feeling for that? Will it be even comparable to the wavelength? Because I feel like if the wavelength is like 2 millimeters, and then yeah, I mean, you can't bend this one. I could bend. This is like a decimeter. Right?
Yeah.
I'm bending. This is my plastic hose. Obviously, it's not the stripe, but the kind of a mock-up.
I think it was several decimeters.
Several decimeters. Yeah. But then there might be other effects. It might not be the signal actually creeping out, but there might be other effects that the thing is just sturdy, so that it'll be hard to bend. It got it. Yeah. But
exactly.
That's actually a different physical effect. It's not the leakage because the radius is comparable to the wavelength, but it's rather that the material itself is so sturdy that you can't bend it.
Yeah. Even the material impurities can make more dispersion or more leakage to other modes. So especially the bandwidth that you mentioned, this is very important. So maybe I can take it later on where we started looking at link budget, speaking of the bandwidth. But the bandwidth can be limited by fiber, for example, as you say, because for a very high bandwidth, you are allowing more higher order modes. And then all these bendings or twisting of the fiber make it more prone to having leakage to higher order modes.
Mm-hmm. I see. So there are this sort of effects that, yeah, I can imagine there must be also other like electromagnetic, or, well, put it this way: if I take the stripe and it carries so this is a plastic stripe and it carries a terahertz signal. Basically acting as a waveguide. So it will have a core, you said, made of some plastics, and it will have cladding, also made but of a different type of plastics. Now, what if I put this close to something like dielectrical, like another piece of plastics, or close to something metal? Would that influence? Could there be like coupling introduced here between the stripe or how well insulated is the core from?
I may be wrong, but I've seen articles that they mention that you try to confine the field more and more in the core, right? It's more than 90% that is confined in the core. And then you have some cladding. There are also extra claddings, which make it more isolated. So I've seen these pictures from conferences that people put their hands and, or as you say, make metal objects closer to this, but they didn't see any negligible. It's negligible, the effect.
That's negligible, the effect. Yeah. Interesting. Okay. And of course, this I would suppose that you would have to sacrifice something, right? I mean, the more cladding you put, the larger, the more the better insulated will the core and the signal be. But the larger diameter, the more sturdy the thing will become.
Exactly.
So,
it's all trade-offs.
Like an interesting trade-off there.
Yeah.
Right. And talking about link budgets, I think we have been speaking about some of the issues with losses inside the fiber. On the other hand, if I remember my basic cone theory books properly, do you have sort of a linear loss with the distance inside a cable or this kind of waveguide, while over there it's more quadratic in line of sight scenarios. So in a way you could, I mean, even without this kind of amplification, you might benefit from sending the signal along the wall until you're close to the user and then send it from an antenna there over the air. Then of course you also compensate for the losses. But talking about then terahertz and link budget over there, how far away do you think we can reach if we have a big machine room somewhere in a factory?
Yeah. So when we started with the use cases, we tried to identify the deployment environment, because as you say, when we have these robot factories or assembly lines, usually the ceiling height is quite high, 10 meters, for example. Then we also had this office space or healthcare environments where you have the 3 to 4 meters of ceiling height. So we use those numbers for our link budget. But as you say, at these frequencies, the path loss for 10 meters is already 90 something dBs.
All right.
So it's
Yeah, I
quite
guess when speaking of the loss in the or propagation along the fibers compared to propagation in the air, one way of thinking about it is, I guess, would be that when we transmit along the fiber, and basically you can think of that as forming an extremely narrow beam, so that after a meter, the signal is only the width of the beam is only like the diameter of the fiber, right? So whereas if we just haven't put an antenna here that transmits omnidirectionally, then field will go in all directions. But within
Indeed.
the fiber, it will go in extremely narrow.
It's more confined. Yes.
Sector. So there'll be an enormous gain in link budget in bringing the antenna closer to the antenna unit closer to the user. Mm.
So I guess this is like a 3-year project or something like that. So looking forward into the next 2 years that you will be working here, from my perspective, who's someone who's not really working with hardware, to me it seems like it's the hardware challenges that you really need to overcome, and maybe prototyping, these type of things. Are these the main challenges, or what will you be working on now?
The fact that I'm also a hardware person, if I say yes, then I guess I'll be criticized by the project partners. No, but I think it's twofold. It's both the hardware, but it has to work, and for us to see if it works, and we can do some measurements. But it is also the system operation of these two frequency bands, and we think that we need to understand the hardware impairments first and foremost, and be able to define the waveforms and the algorithms that these the two systems need to work together with. So I think it is at its core, it's the hardware, but we need to also solve a lot of system questions.
Mm. And I guess there'll be questions of the sort like, what are appropriate waveforms to be used for the terahertz signal, right?
Exactly.
I mean, if we have so much bandwidth available, we might not care as much about spectral efficiency. We might care more about like hardware friendliness. So constant envelope would be maybe the ideal waveform that could enable amplifiers to be pushed up higher towards saturation and operate at higher efficiency. And there's this trade-off between choice of the sign of the hardware on one hand and the sign of waveforms in particular on the other hand.
Right. And for someone who is not into hardware design as well, it might feel like, okay, you just take like a cable and then you take an amplifier and then put an antenna, you put them together like Lego and then you're done. But I also heard this concept of packaging, and which apparently is a challenge. Can you say something regarding that?
Absolutely. Yes, that is indeed a challenge. So let's say we go for higher frequencies and you need more antenna elements. The size of if we have a huge array, we don't have it right now for the tandem. I will explain that later. But let's say you have a huge array and already your size of the array is bigger than your chip, the MMIC that you have. And so then there are many ways to there are many things that you can discuss. There is this where you have the problem with the bandwidth, for example. You have a huge bandwidth and then you have a beam squint, how to do the phase shifters, this and that. And then you have a huge set of devices and circuits that you need to integrate. And then interconnect losses are quite high at these high frequencies. We cannot read, I mean, we are talking about few dBs now on the fiber, but inside the chip, you want to avoid few dBs of loss when you are connecting the antenna to the TRX switches, and the switches are lossy, for example, as well. So you want to bring everything close to each other. And then there is this concept of integrating all of the chips, modules, and the antenna on the same package. So you have, for example, with this technology that we have with the EWLB, embedded wafer level bulk grid array that Infineon has, you sort of put together the antenna, the chips, you have some redistribution, metallization layers to do the routing, but then it's short routing so that you avoid high losses.
So
Already there.
that'll be losses everywhere, basically, and the loss be leakage, I suppose. I mean, it might be one reason why packaging is important here, that anything,
Yes.
any electrical wire of any sort will leak radiation, and this problem just gets worse and worse when we go up in frequency. So
indeed, so you want to bring closer everything to each other, and then here we have the AIP, we call it antenna in package, where you have the chips and antennas on the same package. We put them laterally, like not on top of each other because of this current technology that we have, but you can have antenna on package, antenna on chip. There are all these sort of different packaging techniques.
Different packaging techniques and combinations of this can be designed. So maybe we could return, just before we close up here, to the system aspects of the tandem architecture, where again we have this radio stripe at terahertz that provides spot-wise coverage with very high bandwidths and very high data rates. And then we have the sub-10, can we call that a macro system, or at least a sub-10 deployment, presumably some form of massive MIMO or distributed massive MIMO that provides uniform coverage for users that might not at the very moment have access or be in the coverage zone of an antenna unit from the stripes. So what will this entail for the user terminals, like mobile phones, maybe laptops, maybe, who knows, augmented reality headset or something else? Will they need, like, because they will have to support this dual mode operation, right? So they will need like antennas for terahertz, they will need some sort of beam steering presumably to tune into the closest stripe spot, and they will need sub-10 antennas, which are already there, but there will be some aspects here in like integrating together very different frequency bands. Is that something you could speak to, Parisa?
Yes, of course. So that is truly a very important point, because when it comes to the our link budget and system requirements that we currently are making any assumption, we need to also make an assumption on the UE, because you have the receiving end there, for example. And what kind of gain you have, do you have beamforming capabilities or not? At its basic concept that we have here in 6G tandem, it has to follow both frequencies. It has to have, as you say, sub 10 or sub 6. They already have the mobile handsets, and what we did, for example, with 28 gigahertz, the millimeter wave 5G NR, they also had the antennas to support that frequency. For example, was it Apple or Samsung that they had even two panels of 4 or 5 elements, 5 elements supporting, I don't know, was it dual frequent TXRX, for example, one panel for each. So I think even for tandem, the UE needs to have the sub terahertz frequencies. But then we also have these questions: should they have also beamforming characteristics? Will they have, how many number of antenna elements you can have there? What we did for our link budget analysis, we made the assumption that, for example, if you have for 28 gigahertz, you can have 4 to 4 4 to 5 elements, then maybe you can have 16 elements for 140 gigahertz. And so, but as you say, we don't know if it will be ever realized, because these are very high frequencies. You will have maybe more complicated hardware in the handset. We have to see. It will maybe happen in 10 to 15 years. But then, as you say, there are these very tiny beams that you will get your hands on, where to put the antennas,
yeah,
how
where to put the
do
antennas, right, on the actual devices here.
That
also
yeah.
sounds like a challenge.
But also, you mentioned the head mount devices for the AR, VR, XR applications. Actually, we did a measurement campaign in KU Leuven for 60 Tandem projects. They did some tests with the millimeter wave frequencies, and they see that there is this very big challenge with losing connection because you're moving your head very fast. There is this rotational speed. We should really be aware of all these. Maybe for the head mount devices, you have to have more coverage on the head, or so not just one element. It should be maybe.
No, right. I mean, then you'd have to point your nose just straight to the access point. You probably, or antenna unit, you probably want antennas all over the place, right? So you can keep the visual line of sight direction to Taylor Swift, and then at the same time you got your antenna panel line of sight to the pointing to your to your stripe.
Yes.
Right. So it seems like there's a lot of experimental work that needs to be done in order to realize this vision here, which is both in terms of hardware testing and simulation work, because of course we can't have all of the hardware available before we start to planning things, and also to know how you would like to build things is good to do simulation. So what are the kind of tests that you see on the agenda?
Yes, for the validation of the tandem system, we have to start first simple with the hardware itself. So we are envisioning to have like to test the hardware in the Kohlberg laboratory in Chalmers, where they have very high-end instruments. You have the probe stations to probe the package or the chip, to test the chips, and then you have the packages where you can connect them to the arbitrary wave generators and the up converters to generate the signal. So it's a lab test essentially, and at the other end, where you so you have the radio units, you have the fiber, another radio unit, and then you couple it to an oscilloscope, a real-time oscilloscope, to see how the system works, this hardware system works. And probably we will have 2 of these parallel fibers and radio units to see how they work together, maybe do some over-the-air tests. But then we have this tactile test bed in KU Leuven, where they have availability, maybe I'm wrong, but it's what's quite high number, 280 of sub-6 units that you can try different constellation of distributed units. You can have vertical, ring, or horizontal. So we aim to have some tests there, trying to make measurements of the channel and do some ray tracing modeling together with the hardware that we have measured here for the sub-terahertz. So we really need to have a modeling framework to see how these things work together, because you cannot have that by the end of the project, the whole hardware system to do the tests. So we need to make compromise and use the hardware measurements and the testbed measurements to have some input, do the modeling framework, employ the ray tracing, and also from the UE side, we need to have some application requirements and mobility information, how it will be for the specific use case, to make a simulation of these two. I've been actually also thinking about some commercial tools. Maybe we can use that, because now things have evolved really. So we will see what we can do. But of course, we have our ray tracing tools, open source tools as well.
Right.
Yeah.
So I have run out of questions here. Do you have anything else to ask, Eric?
No, I think it might be time to close up here. Thanks a lot, Parisa. This has been fun and very educational. Thanks, Emil. And see you all next time. Bye-bye.
Bye-bye.
Bye.